you have been taught a Newtonian mechanics. Newtonian mechanics. You have been studied and only Newtonian mechanics. And today, I'm going to teach you a kind of a very powerful tool which can be used rather than the Newtonian mechanics, right? This is called Lagrangian mechanics, right? Lagrangian mechanics. Okay, before that, this is the outline of today's presentation, of today's lecture. And throughout these segments, what I like to teach you is the concept of and the fundamentals behind the Lagrangian mechanics. Right now, you know another mechanic after this lecture, right? Actually, I know about the Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics, and quantum mechanics, and classical mechanics, right? But you only know about only Newtonian mechanics, right? So throughout this course, I expected to finish until up to Hamiltonian mechanics, right? That is the maximum amount of thing that I can give, right? You can in these lectures, you don't have to be worried about the quantum mechanics or classical mechanics involved in the general theory of relativity, right? Okay, let's start. This is the introduction for the Lagrangian mechanics. So another portion of lesson have to be conducted how to practically use this mechanics, right? Throughout the today's lecture, what I like to teach you is how to understand the Lagrangian mechanics using the formulation, right? I mean, I'm going to derive the Euler Lagrangian formula to sake of your convenience of knowledge, right? So let us consider very simple case. In most of your day-to-day life, you may involve these kind of activities, jumping, right? So throughout the jumping, right, you may never assume, you may never imagine what will happen, right? So let us consider the following definition. So kinetic and potential energy, right? Here, the kinetic energy of some point can be shown to the function of the velocity, that is qt dot. Qt is represent the position, right? Position vector, magnitude of a vector, right? So qt dot represent a velocity. If the qt is the position, t dot is the velocity, then the kinetic energy of an object can be assumed as half me q dot square, right? Which is intuitive, right? The potential energy is a function of the position. We know that the potential energy is nothing but mg time of the displacement. That means mg qt is the potential energy of the object, right? That means if this person is jump, right? At the beginning, we can have the maximum kinetic energy, maximum potential energy, which is the potential 0 point, right? This is the potential reference, right? We have the maximum potential energy and minimum kinetic energy. That means we can have zero kinetic energy. In general, we don't say that zero, right? We just assume that the minimum, right? At at some time after jump, we will make the point with the kinetic energy is equal to the potential energy. That means at the point B, we can have equal kinetic energy, and kinetic energy will equal to the potential energy, right? So at the end of the day, we can see that the potential energy is going to be minimum at this point, and the kinetic energy is have been the maximized, right? So now I'm going to introduce kind of another concept called Lagrangian parameter, right? L. We usually donate the L for define the Lagrangian, right? Let us define the kinetic potential, that means the energy difference of kinetic and potential energy, often called the kinetic potential. That means the Lagrangian is nothing but kind of a kinetic potential. The Lagrangian will depend on time, position, and the velocity. Okay, velocity, the time, position, and velocity. Therefore, we can define this statement to represent a kind of a Lagrangian, right? For all kinetic potential energy translation, we consider L as a Lagrangian. That means throughout this motion, we can observe kind of a kinetic potential translation, right? Because the amount of potential energy have been converted into the kinetic energy, and energy will be maximized at the end of the day, and the potential energy will be minimized, right? Therefore, there is a kind of a translation between kinetic and potential energy. If this man is down under the gravitational field, right? So now you know that what is the Lagrangian, right? And now we can further study the behavior of this Lagrangian, right? So I'm going to define the concept of action in the motion, right? Action in the motion. So here the energy translation to the motion under the conservative vector field. What is the conservative vector field? Conservative vector field means, for example, a unique force field like gravitational field, right? A conservative vector field, right? Conservative vector field means kind of a unique vector field. The meaning of the conservative you will study in the further lessons, in the future lessons in this course, right? So if you have trouble to accept the term, the conservative vector field, right? You can assume that force field like a gravitational field, right? And the Lagrangian of this matter, we consider the motion under the unique force field, right? First of all, Lagrangian have been positive. Sorry. positive near. No. This will be other way around, right? First of all, at t is equal 0. Okay. This is wrong, right? This must be negative at the t is equal 0 because the potential energy is maximum in here, right? However, this is kind of a general. This is kind of a general translation. We assume that the kinetic energy, the other way around, right? We can if we consider the motion the motion of a projectile, right? Vertical projectile under the gravitational field, right? We do have very huge kinetic energy at the beginning. If we refer to the if you refer the energy reference to the ground, there will be no kinetic energy, no potential energy at the beginning, right? That means if we throw a stone towards to the sky, right, we can have the very large kinetic energy with less, actually no potential energy if we consider the Earth as the reference point for the motion that we consider under the conservative vector field. That means under the gravitational motion, right? So this will be positive at the beginning if we throw a stone towards to the sky, right? And eventually it will reach to the maximum point, right? Maximum point, and there will be no kinetic energy at all, right? And the Lagrangian become store all the energy into the potential energy, and this part will be 0. Then after we receive the negative, right? Negative, and it will reach to the maximum point to the sky before the fallen, right? And here we can observe that, like, for every and each motion involved to the under the motion of the conservative vector field, that may go kind of a force field. Every and each Lagrangian will be go positive to negative or negative to positive. For our example in here, right, it will go negative to positive, right? Here I have been considered kind of a general statement, very high kinetic energy at the beginning, and it will store into the very high value of potential energy. So this kinetic energy will be stored into the potential energy, right? Therefore, we have negative Lagrangian at the end of the day. So every and each motion, for example, if we throw a stone like this, right? Okay. For example, if we consider kind of a stone throw, right, toward to the sky, right? Then at the beginning there is a high kinetic energy, and it will suddenly become no kinetic energy at all. Everything is stored into the in between there is a place kinetic energy will equal to the potential energy, right? And this point, right? This is the point which kinetic energy will equal to the point will equal to the kinetic energy will equal to the potential, right? This point, and then after it will flow into the reach to the maximum point. There are no uh, there are no there are no more any kinetic energy. Then the Lagrangian becomes negative because we have very small amount of portion of the kinetic energy rather than the potential energy, right? So Lagrange, everyone is Lagrangian in the motion considered to the conservative vector will go to positive to negative or negative to positive, and it's kind of a symmetrical function, right? So the important observation about the Lagrangian, we can note that the time average of the Lagrangian will be 0, right? Also, average for the symmetrical time range around the 0 point of the Lagrangian, that means here to here, if we consider the symmetrical time period here to here, the average will be 0, right? Therefore, what we can see is, right, T naught, some T naught to T1 symmetrical time range around the 0 Lagrangian also have 0 average. Okay, and this is the geometrically we can show that the symmetrical time range around the 0 Lagrangian point, that means T naught to T1, right, have the average of 0 Lagrangian because the area under this shaded into the pink color is same as the area under the area shaded into the pink color in the other triangle in here, right? Because these two are positive and negative, these are cancelled out, right? Now, concept of action in the motion, right? Throughout the Newtonian mechanics, you just study the concept of time, position, and energy. And here we will introduce the concept of action into the motion, right? Action into the motion. Here, this part in the average statement, this part is nothing to do with the average, because since average is 0, this part, this time interval is nothing to know any meaning. So we remove this part from the statement and we will introduce the time integral of the Lagrangian as a S is called the action of the motion with some time range. That means that the energy translation between the kinetic energy to potential energy of the Lagrangian integration called the action of the motion, right? Under the motion of the conservative vector B, for example, gravity, we can assume that we can have minimum S, right? Minimum action, and mathematically it can be related into the integration of the Lagrangian of the action is 0. මේක ඇත්තට ළමයි හරියද? මේ the Lagrangian is always 0. Average of the Lagrangian is 0. Therefore, integration also 0 because we do have the negative area and positive area. Both area will cancel out when only if it is considered into the conservative vector field. For example, under the gravity, right? the kinetic energy of an object will be stored into the potential energy and vice versa. So we can have zero Lagrangian throughout the motion. I mean zero average of Lagrangian throughout the motion. That means the integration of the Lagrangian always is right. Now there is a person called the Lagrangian in France, right? Before the Lagrangian, the Euler is found this formula, right? So join together, we state that there is a formula called the Euler Lagrange formula, which can be satisfy these criteria, right? It can be satisfy these criteria and introduce new kind of a mechanics into the physics, right? It's called the Euler Lagrangian mechanics. In Newtonian mechanics, you can have F is equal ma, right? The Euler Lagrangian mechanics, or that we call Lagrangian mechanics, after the most of the Lagrangian work, right? Lagrangian mechanics, we can have another equation which can do everything, right? Without F is equal ma, without the equation of motion. In the Newtonian mechanics, we can simply illustrate all the derivation that we obtain through involved into the mechanics, right? So, and this is the introduction of Lagrangian and Euler Lagrangian formula, right? For conservative vector field. The conservative vector field term is important, right? That means, Katrika, you guys are already covered those conservative vector fields in mathematics. Hello? Ratnayaka?
No, sir.
सांस्कृतिक वाले टेस्ट के लिए का कर लगी ना
No, sir.
the Newtonian mechanics कर लगी ना hello
No, sir.
Newtonian mechanics कर लगी ना
No, sir. No.
ये क्या है मोनोक्कत करना तो लेवल 4 है Euler physics और Newtonian physics कराए whatever, right? In Sinhala we call सांस्कृतिक वाले टेस्ट क्या है I don't know whether at the level 4 you must cover those Newtonian mechanics things, right? Hydrodynamics, Newtonian mechanics. Without things you can't be mechatronic engineer, right? However, let's continue, right? There is another mechanics what I have been talking about the Newtonian mechanics. Then after the major breakthrough for the Lagrange, right? Works of Lagrange, we introduced the Lagrange mechanics, right? In the theoretical issues behind the derivation of the Euler Lagrangian formula. Euler Lagrangian formula is a kind of a statement as same as we use F is equal ma, but for different parameters, right? This formula is derived the optimal path for the average position, right? Average position for action of the object move under the conservative vector field. That means we obtain the optimal path for that means most possible path of the motion, right? This provides a new kind of mechanics for physics of motion of an object, right? That is, we can have kind of a alternative mechanics for Newtonian laws of motion, right? And that is the second thing. Here it is expected to approach unknown optimal path for general geometry of a curve of the magnitude of the position vector, right? Right. And let us consider object moves. This is the magnitude of the position vector, right, as the variable function of the time, right? So let's consider some time period t to b, t naught to t1, a to b points, right? Then therefore the position vector will vary with the time, can be corresponded to these joining curves between A and B, right? Then we can have various kind of paths involved to join these 2 points, right? That means the magnitude of the position vector will vary with the time, can be assumed to the different curves, right? The magnitude of the position vector can be varied for these different representation of the curves. In here, we can have the optimal time variation for the position vector, right? That is the issue. That is the thing that we need to find, right? Okay. Now let us assume that the axis optimal path q bar gives zero action in the motion, right? This is the concept of the things under the concept of optimal curve, right? We can assume that there is a zero action. That means the integration of the Lagrangian will be zero, right? For convenient representation of the general path of the position, we assume that the qt is the general. That means in general we call the position variation as a qt, right? So now the simplified picture of the optimal curve q bar. This is the q bar. That is the optimal bar, and this is the kind of a general path. Can be assumed. That can be anything, right? That is kind of a curve, general curve. That means a general motion of the magnitude variation of the position vector, and this is the thing that we need to find, right? This is the we have to find a condition to obtain this general behavior, the zero action, right? That can be, you will understand, right, why we look after this, the general part of time variation. And when this is not position, this is time variation, right? Qt is the magnitude of the position vector. You know position vector, and the position vector will be changed throughout the time. And this is the optimal path, and this is kind of a in general, right? In general thing. So once we have that, we define the small quantity of the variation of position vector called delta of qt, very small function, and these very small functions called delta function, right? And this is not back delta notation. This is the delta function in variational calculus, right? This is the operator. You can see the square bracket indicate something else. However, this thing is meaning for very small functional behavior, right? And the boundary conditions of a neta function can be assumed, right? Here we define the difference of very small functional behavior for kind of a epsilon value and a positive definite function. Positive definite function means for all the value of t, neta is positive, and the epsilon can be anything, negative or positive, right? So, so we define these small functional differences, right? Small functional difference as the difference between our optimal path and general path, right? And if we go further, right, the difference can be well treated using the multiplication of epsilon and neta t for some unknown functional behavior. For example, if epsilon is 0, we don't have the difference between these two functions at some time, right? So very comprehensive study can be achieved if we use this function, right? Now we define the boundary condition also, right? So boundary conditions of eta function can be assumed for t is equal t0 and t is equal t1. That is the boundary condition can be assumed to this time segment and this time segment, right? We know that whatever the value of the epsilon, eta must be 0 because the optimal path and general path is coincident with both point A and B. So therefore, if we substitute t0 for the difference equation at some epsilon value, we must have 0 because these 2 points are same for both general curve and the optimal path, right? That can be assumed to the same boundary condition for B also. So therefore, we assume this boundary condition for eta function. That means when t equal t0 and t equal t1, the concept of this unknown function neta will be 0, and we know that this neta is the positive definite function, right? These are the definition which we need to treat down this problem, right? So this is the concept, right? For the relationship between the average or optimal path and the general path, right? So the difference can be geometrically represented as the delta function of q, right? The delta function of q. Since this delta function, this is the summary, right? Summary of the relationship, right, between the q bar and q. That means the optimal path and general path. We have developed a different formula for total difference as relationship of between optimal path and general path, and the difference statement represent the delta function, right? Delta function. It's very small functional variation. Also, we can assume that if for some real value of epsilon, real value means that can be negative or positive, right? With some positive definite function, which is unknown function, but we know the boundary values as well, right? So we introduce this difference as multiplication of both epsilon and zeta, right? So we can well treat these differences, right? At the end of the day, we can propose a joint statement, right? Where the difference function, the difference can be treated as this way or either this way, right? So we can use two equivalent signs, right, to represent the difference, definition of the difference, as well as this functional behavior for some well-known definition of the function, right? For real value of epsilon and positive definite function theta, right? These are the boundary conditions, right? These are the boundary conditions, and we know that these two guys are going to be zero as we define in here. So this is the summary of the definition. With this definition, we will study the action of the Lagrange integral, right? And here we can assume the first order Taylor expansion, which I have introduced in the other day, the lessons, right? The error or total difference between the of the Lagrangian can be treated as the difference function, right? Can be treated as the small segment of the Lagrangian, right? This is a very small segment of the Lagrangian. Can be derived using a first order Taylor expansion, right? Now, now the thing can be mathematically treated, right? As we obtain the integral for the very small segment, because we have been introduced the Lagrangian for this notation, right? That means very small portion of the Lagrangian sum can be equal to 0 under the conservative vector field, right? So this sum here is equal and opposite for the sum of the small segment here, right? The delta of the Lagrangian can be assumed for very small portion of the Lagrangian value, right? So then we have been introduced a Lagrangian as the sum of or integration of very small Lagrangians over the period, right? Over the period. And therefore, right, first of all, we have to consider the very small segment in the Lagrangian that we introduced in the previous slides, right? And what we are going to do is we're going to integrate for some every and each small Lagrangian as we done in here, right? Done in here. You can see that this black box represent very small portion of Lagrangian at t is equal t naught time. And we're going to sum here to here, and it is equal the summation of here to here, and but but this sum is negatively equal to this sum, and the summation will cancel out and it will become 0 for conservative vector field, right? So we need to obtain the very small portion of the Lagrangian. Therefore, we can consider very infinitesimally small position part. We do have infinitesimally small velocity part. Then it will produce very small segment of Lagrangian, right? According to the definition of the first order Taylor expansion, we can obtain that. We can mathematize the problem of very small segment into the introduction of the first order Taylor expansion, right? So if you sum this small segment over the time T0 to T1, right? Then we will end up with this integration, right, in the right hand side, and this is the problem that we need to tackle, and this is the same as our action now, right? This can be considered as the action, but we will check this form, right? Then action can be obtained to the integration of this using a first order Lagrange, first order Taylor expansion of the Lagrange, right? At some time value, right? At some fixed time value, right? That means we assume that T is constant, the value of the QT will be dragged, right? These kind of a treatment called variational calculational treatments, right? For some T, we will drag the value of QT, right? We assume that QT can be assumed variable, right? So this is the kind of a variational calculation treatment for the Lagrangian statement, right? And we obtain the action of the motion to this statement number 4, right? Now we can actually treat that part there, this integral part as shown in below. If we understood well what is the delta of Q dot, that means the small variation or behavior of the velocity, right? Now let's see, since Qt is the function of time, right? We can differentiate the statement of the original statement of the difference formula, right? The time derivation of this statement can be considered as into this form, right? So if we consider this part, this is nothing but the delta difference of its velocity part, no? Right? Then the differentiation of the difference, functional differences can be considered as the differentiation of difference, right? So we found a method how to treat the delta Q dot part, right? So delta Q dot part is nothing but this, right? As same as this part, right? So now we can substitute that thing into this integral performed due to this red color functional part, right? So the statement number 7 can be arrived throughout these tactics. Okay. Then after what we can do is we can use the part by part integration method to simplify this statement into the statement number 8. and using the boundary condition that we assume the 2 point of the A and B, right? We know that this is nothing but theta T naught and equal theta T1 equal 0. For these two parts, the theta function is 0 from the definition, right? Therefore, this integral in front of this part by part derivation is nothing but the substitution of this, right? Therefore, this is 0. This part is 0, and the integral, the simplification term of this integral can be considered the negative, the rest of the part, right? Then we can substitute this part again into the here, again into the forming integration into the here, right? Then we will simplify this into this form, right? And now we can have the action into the differential functional performance. Also, we know that we can remove this the difference function, difference delta function, so delta function in terms of epsilon eta terms, right? In terms of epsilon eta terms, we know that this eta is nothing but positive definite function, right? And the epsilon is the variable which can be moved, which can be changed the behavior of the general curve towards the optimal path. If the epsilon is 0, this will going to be glued together, right? Gaps in the two function will be disappear if the epsilon is 0. But however, now we can have the action of the motion into the statement number 11. The statement number 11, this the left hand side of the equation is nothing but the action of the motion, right? Then action is equal to this the rest of the thing, right? This part. Then for optimal condition, what we have to do is we have to derive, we have to consider the differentiation to find the minimal point of the action, right? Then we simply equal to the 0, right? So now if we differentiate the epsilon, we will find the optimal condition for that as same as the statement number 13, because the epsilon is only appearing here, right? Then once differentiate that, this will disappear from the equation, right? Then we can have the optimal condition with the statement number 13, right? Now we know that theta is nothing but the positive definite. That means whatever the value of t, theta will remain positive. And now we can cancel out, right? And then rest of the thing must be 0, right? To 0 this integral into the its value, right? So now we achieve the condition for optimal path for this statement called the Euler Lagrange formula in the mechanics, right? Okay, let me finish this, right? And if we have enough time to clarify them, right, we will discuss, right? So using Euler Lagrange formula, this is called Euler Lagrange formula, we can deduce the equation of the motion also, right? So let us assume the motion of an object under the conservative force field. That means the conservative vector field. Force field is also vector, no? Because conservative force field of conservative vector field, right? So the conservative vector can be shown as the arrowheads of field, which drawn in into the blue color, right? And this is the position vector now. Position of the object. The object of mass of m have the magnetic force of m towards the r direction, right? Then we consider the motion from the position vector of ax prime to, that means a to b, right? To derive the equation of motion using the Lagrange formula, right? So now we can consider some very small displacement, right? We can consider very small displacement, and that displacement can be shown to the statement number 15 using as a vector, right? Now capital H is a, you know, if you use the something into the capital form, it will represent a vector, right? Both capital form is vector, and also we can derive the velocity using into the velocity of the object using this using this the position vector, right? So this is the position vector, and this is the velocity corresponds to the position vector, where the ax part is nothing but a constant, that is the initial position of the object. That means this mass is moved through this arrowhead a to b, right? And now we can perform the parts of the kinetic energy and the potential energy. Potential energy for work done. Work done is nothing but the magnitude of the force into the displacement, right? That is the work done. Since this object moves to the opposite direction of the vector field, right? There is a negative work done can be assumed, right? The negative work done can be assumed to the potential energy, right? And the modulus form represents the magnitude of the displacement, right? And the kinetic energy is nothing but half m q dot squared, and we can perform a Lagrangian to kinetic potential into the statement number 19, right? Now here we can actually obtain the requirement of the Lagrangian. Requirement of the Lagrangian Euler Lagrange formula. In the Euler Lagrange formula, we need to find this part and this part, right? So throughout the simplification, we can show that the Lagrangian due to the position, the different partial differential of the Lagrangian of the Lagrangian is nothing but the magnitude of the force, right? Also, if we consider this part, this partial differential coefficient of the derivation, right? Differentiation of the time, right? Is nothing but this part is not depend on the q dot. Therefore, if we differentiate this part into q dot, this is nothing but m q dot, right? because 2 is cancelled out, right? Therefore, daba L by daba Q dot is nothing but MQ dot, right? And if the MQ dot is differentiate throughout the time, right? This will become, this dot notation become double dot, right? Then we can perform the requirement of the Euler Lagrange formula, right? Using this form, right? We know that the left hand side of the form must be 0 due to the Euler Lagrange criteria that we have been deriving here. Okay? So at the end of the day, we can have the abstract proof for F equal MA type solution, right? So in the Newtonian physics, Newton just assumed this criteria linked to the force. That Newton defined the force without telling anything, without telling anything, right? But we can have comprehensive picture of the proof of the equation of the motion, or F is equal ma, using the Euler Lagrange formula, right? In the Newtonian mechanics, this is the basics. But in the Lagrangian formula, we can tell more than F equal ma, right? And that will end today's short part of the lecture. Now, time for questions and answers for any clarifications. Okay, මොනවද තියෙන ප්‍රශ්න ඔයගලන්ට? කාටද ප්‍රශ්න තියෙන්නේ මේ ගැන? Matthews, you have problem? Pushpakanta, you have problem? This is going to be an exam question, right? I mean, the assignment question. You guys must submit assignment today, right? මොනවද තියෙන ප්‍රශ්න ඔයගලන්ට? කාටද ප්‍රශ්න නැද්ද? චන්ද්‍රිකා ප්‍රශ්න නැද්ද? Hello.
Regarding this lesson or the assignment?
No. The very next assignment, Euler Lagrangian going to be play a question in your assignment number 2, right? Assignment number 1 submit කළා නේද හැමෝම? චන්ද්‍රිකා? submit කළා නේද assignment එක? දැම්මනේ අද නේද දාන්න තියෙන්නේ? ඊයේ දාන්න තියෙන්නේ. assignment එක දැම්මද ඔක්කොම? මේ ළමයි කවුරුත් කතා කරන්නේ නැහැ. ඔයගොල්ලෝ නැද්ද lecture එකේ? Hello? Hari, now we will stop here, right?
Excuse me, sir.
Yeah.
Some of the question we couldn't finish in the assignment. So is there any possibility if we able to finish those and submit again?
That will depend on the department regulation, right?
Okay, sir.
So what kind of amount of marks will be reduced if per day, I think? මොකද? Hello?
Okay, sir.
චන්ද්‍රවන් කරේ නැද්ද assignment එක?
සමහර වෙලාවට කරගන්න බැරි sir.
ඒකේ තිබුණේ මොකොත් තිබුණේ නැහැ අලුත් පාඩම් කරපුවා මොකද තිබුණේ?
නෑ මට ගොඩක් lectures එහෙම miss වුණානේ.
ඉතින් මාර මේ ලෙක්චර්ස් ටික මේකේ තියෙන්නේ.
ඔව් ඔව් බලන්න ඒ මගේ වැරද්ද තමයි ඉතින්.
දැන් මෙහෙමයි ළමයි. හරිද? ඔය එක assignment එකක් කරන්නේ මාසයක් කල් දීලා තින්නේ. හරිද? මාසයක් කල් දෙන්නේ මාසෙම වැඩ කරන්න ඕනේ assignment එක දාන්න. නිකන් අතට එන්නේ නැහැ. හරිද? ඔය කවුරු හරි කෙනෙක් නිකමට හරි ඔය assignment මේ දාන සයිට් ටික ලෙක්චර්ස් ටික බැලුවා නම් මේ එතන අලුත් ප්‍රශ්නයක් නැහැ. ඒ කරපු එකක්මයි අහලා තියෙන්නේ. නේද? සඳරුවන්?
Yes sir, I knew that. Only
Yeah,
thing I
There are
didn't
no
manage
such
time.
thing new questions. නේද? ඇත්තටම මොකෝ ප්‍රශ්නේ? why දැම්මෙත් නැද්ද assignment එක?
දැම්මස සමහර ප්‍රශ්න නැතුව ඒ කියන්නේ සිමුලේෂන් පාර්ට් එක නැතුව ඒක
ඉතින් ඔක්කොම මේකේ තිබුණානේ. ඒකේ අහලා තින්නේ ඔක්කොම ප්‍රශ්න මේ පරණ ලෙක්චර්ස් වල තිබිච්ච ඒවාමයි අහලා තියෙන්නේ. අලුතෙන් කිසිම දෙයක් නෑ. අලුතෙන් හිතන්නේ ඒවා. නේද? ළමයි? ඇයි පන්දුවන්නේ ඉතින් සීනි බෝලේ වගේ එකක් නෑ. ඉතින් මේ දීලා තියෙන්නේ. ඉතින් ඒ ටික ලියලා අර ටික බලලා මේ පොලේක ලියන්න විතරයි තියෙන්නේ. නේද? මොකක්ද ඔයාලට තියෙන ප්‍රශ්නේ වනේ මොකක්ද කියන්නේ? මොකද ඔයාලට මේක ඩවුන්ලෝඩ් කරගන්න කරනවා?
නේස ඩවුන්ලෝඩ් කරා ඉමිඩේට් කරගන්න.
මේනන් ප්‍රශ්න තේරුම් ගන්න අමාරු නෑ එහෙමයි. එහෙමද?
ඔව් සර් මොඩලින් ගණිත පාර්ට්ස් ටිකක් ගොඩක් දුරට කරා සර් සිමුලේෂන් එක මට ඇත්තට මගේ වැරද්ද සර් මට වෙලා
සබක ඒ කියන්නේ එකලා ඔයා විතරක් දැම්මේ චත්‍රිකා විතරක් දැම්මේ. දැන් ඔයගොල්ලෝ යාළුවොත් එක්ක කතා කරලා නෙමෙයි assignment කරන්නේ. ඈ? අනේ මන්ද. මේමයි ළමයි හරිද? ලකුණු 50ක් තියෙනවා ඒකට. ඊළඟ එකට නම් දෙලින්ම බේස් වෙන්නේ කරපු ඒවමයි ඈ. මම ඔයගලන්ට කියවන්නේ මම අලුත් ඒවා දෙන්නේ නැහැ. So I don't like to put you in trouble, right? So I only consider what I conduct to my lectures. නේද? මම මේ අහලා තියෙන ප්‍රශ්න එකක්වත් නැහැ පිටේ ඒව ළමයි. පත්‍රික මොන හරි කියන්න ගියාද? මොකක්ද ප්‍රශ්නේ වගේ? අලුත් ප්‍රශ්න නම් දාන්න නෑ දරුවා. හරිද? මේක තියෙන්නේ previously කරපු ඒවා. ඊළඟ එකෙත් තියෙන්නේ previously කරපු ඒවා. මම කියවනේ මම කියලාමයි දෙන්නේ. මේවා එනවා. හරිද? ඒ කියන්නේ මට අලුතෙන් ප්‍රශ්න ඇහුවොත් ඔයගලන්ට කොහොමද කරන්න බැරිද? ඒකින්ද මම මේ තු ඉගෙනන එකක්මයි දෙන්නේ ආපහු. හරි. Okay, now time is right. That will end to today's lecture, right? Those who are unable to answer the assignment, right? The amount of marks will be reduced per day, right? Per day, according to the department decision, department regulation. I can give you a fair chance, right? Amount of marks will be reduced per day, for every and each day for delays, right? But whatever you did, you must submit assignments, right? Without submission, I can provide you amount of eligible for the pass marks to the department, right? දැන් මේ තේරෙනවනේ ළමයි. චතුරිකා තේරෙනවනේ කියප එක.
Alright sir, I will inform others also.
ඔව් සර්
අනිවාර්යෙන් ළමයි දාන්න ඕන assignment එක. right? නැත්නම් එළිය මේක පාස් වෙන්න බැරි වෙයි. මම කැමති නැහැ මාත් එක ගාලා ළමයි ෆේල් වෙනවා. මම කිසිම යුනිවර්සිටි එකක ගන්න ප්ලෑන් එක ෆේල් කළා නැහැ කවදාවත්. මම ඔයගලන්ට කිව්වනේ මේ කරෝප එකම තමයි දෙන්නේ. මේක ඔයගලන්ට දෙන්නේ මේ මොකද්ද ඒ කියන්නේ ක්වෙස්චන් එක බලලා ක්වෙස්චන් එකට අදාළ ලෙසන් එකට ගිහිල්ලා බැලුවොත් ඔයාලට තේරෙයි. හරිද? මම එතනින් එහාට වෙන මොනවක්වත් කියන්නේ නැහැ. වෙන මොනවත්ක්ම කළා නෑ. වෙන මොනවත්ක්ම ස්පෂ්ට කරලා නැහැ ඒක. ඔයාලට ඉන්නේ ඒක නම් අලුතෙන් මැත්ස් හිතන්න දෙයක් නෑ. ස්වරූපය එකමයි. මොකක්ද ඒක කියලා තේරුම් ගන්න විතරයි තියෙන්නේ. හරිද? හරි. Let's wind up now. Okay, thank you for your